athletes, whoop whoop. All right, let's do this. Okay. Here we go. Take a minute, look at this warm up. You need to look at these, try to create a rule, and then just write down the domain and range in the little curly brackets. Ready, set, go. I don't have any coffee today, man. I'm gonna drink some Pepsi. All right, I'm going to assume you paused it, did what you needed to do. I'm going to start moving on. All right, when I look at this, I see that for each of these x values, the y is opposite. So I know it's y equals negative x. Okay? All right, so my domain is just all my x values, which is 3, 4, 6, negative 7. Don't worry about order for domain and range. For range, it's negative 3, negative 4, negative 6, and positive 7, exactly the opposite, right? All right, let's look at number 2. The first one doesn't help me much. Second one, I see x times 3 is 12. 2 times 3 is 6. Negative 1 times 3 is negative 3. So it's y equals 3x, because I'm multiplying x times 3 each time. And my domain is what? 0, 4, 2, negative 1. My range is 0, 12, 6, negative 3. Boom. Let's look here. See, 2 goes to 1, 8 goes to 4, negative 6 goes to negative 3, 1 goes to 0.5. We're dividing it in 2, so it's y equals x over 2. Boom, right there, look at that. And my domain, again, just do the curly brackets, write all your x values down. 2, 8, negative 6, 1. The only big thing to keep in mind is if there's ever a repeat, you don't write numbers twice, just write them once. Okay, for range, it's going to be 1, 4, negative 3, and 0.5. Let's look at this one right here, a rule. See, it goes from 8 to 7, 0 to negative 1, 4 to 3, negative 1 to negative 2. That's subtracting 1 each time. So it's going to be y equals x minus 1. Boom, that's the rule. And my domain is going to be 8, 0, 4, negative 1. Boom. And my range is just 7, negative 1, 3, and negative 2. Boom. Super simple, guys. Nothing big. All right. We're going to move on to some vocab, y'all. Let's get into this. We actually got a lot of slides to go through today. It's going to be very little writing, lots of slides. Well, I mean, you're going to write stuff from slides, but very little following me along. So here we go right here. You should have linear function, linear equation, intercept, line symmetry, and point symmetry. And we're going to ignore the rest. Oh, what happened there? We're going to ignore the rest. So just write those down. Pause this. I'm not going to stick on it very long. So you have the power of pause. I'm moving on. Ready, set, go. Oh, let's look right here, guys. I'm just going to scroll down here. The difference between linear and nonlinear. Okay, we see linear functions can be written in the form of f of x equals mx plus b or y equals mx plus b. Nonlinear functions cannot. Some examples of linear functions are that should say f of x equals 3x minus 5. I just wrote it terribly. It should say f of x equals 3x minus 5. There we go. Or we have y equals 2/3 x plus 1/2. H of x equals 3.2x plus 6.25. 3x equals 9 minus 2y. A graphical version of a discrete function is just like a straight line right here, right? Linear function, it's a line with dots. Continuous function would be a straight line like that. Perfect. Over here, examples include that are not linear. 2x squared, anything with x squared in it. Anything with x cubed in it. Now, the square root is not what makes this function not work. It's the fact that x is under the square root sign. X is under the radical. You can have, like, I could have y equals the square root of 5 times x plus 2. So that x isn't under the radical, just the 5 is. So that would be fine. So just a distinction there. Anytime x is in the denominator, it's not going to work. Also, anytime you have x times y, that's not going to work. So just keep that in mind. They kind of killed 2 birds with 1 stone. And you see these are not linear, clearly curves to both of those. Okay? All right. We're going to go through a bunch of slides now, so I'm going to switch back there. And I just want to talk you through it again. It has to be able to be written in the form of y equals mx plus b. You see right here, we work it down from 6x minus 5 over 3 to 2x minus 5 over 3. Pause this to take a look at the process if you want to, but my biggest concern is that you just see that we can manipulate this into that. Don't just assume because there's a fraction there something's wrong. The same way right here for b, notice right away, guys, this is a non-starter. As soon as there's an exponent that's not 1, which you don't see if there's always an exponent of 1 on x, it's nonlinear. Right here, we see x in the denominator. That's not going to work. It's done, nonlinear. Right here, this is in standard form. The ax plus by equals c, that can be made to be y equals mx plus b, so that is a linear function. Okay. All right, let's do this together. We're going to look at some of these. Yeah, there's a number in the denominator, but that doesn't matter. This is absolutely linear. Does everybody see how there's an xy there? Nonlinear. Can't have x times y. It doesn't work. H of x equals 5? Absolutely. That is actually a horizontal line at y equals 5. It's linear. F of x equals 3x squared plus 2. Nope, there's an x squared. Doesn't work. 3x plus 5y equals 8. Yeah, absolutely that works. And look at this one. I bet you were thinking it doesn't work, but that square root is just above the 3, not the x. This absolutely works. Let's check our answer. Boom! That uncomfortable noise that we love. Awesome. I think that's all there is on this one. Okay, let's go to the next. All right, looking at this one. Yeah, there's no straight line that can contain all this. This is not a line, straight line. This, however, I can connect with the line. Let's look at that. See how a straight line can go through that? It is linear. So nonlinear, linear. Boom. Let's flip it back, though. Okay, let's select all the graphs that are a linear function. Notice I could do a straight line through this. That's linear. Clearly not a straight line, not going to work. Again, there's a curve, not a straight line. Yes, this is horizontal. D is a straight line. Look at that. We did it. Boom, boom. Shake the room. Just occurred to me, why was I not in full screen mode? So now I am. Okay, let's look at this, guys. So we have, Michaela has started working part-time at the local hardware store. Her time at work steadily increases for the first 5 weeks. The table shows her total earnings of those weeks are her weekly earnings modeled by a linear or nonlinear function. Well, down here you'll see this has already been graphed. This is the weeks down on the X and the earnings on the Y. And we see it plotted right here, so let's go ahead and just connect 2 of the dots. If we can connect all the dots, I'm just going to do the first and last. If all the dots line up in between, boom, like that, it is a linear function. Yay. Look at that. Okay? So this is indeed a linear function. All right, awesome. Bailey and Carlos are taking a 150-mile bicycle trip. The table shows the distance remaining after each hour of cycling. Is the distance remaining modeled by a linear or nonlinear function? Well, let's find out. Every time it goes up an hour, let's see, this goes down 150 to 128 is 22, right? 128. If I were to subtract 22 from that, hopefully it gets me here. Let's see, minus 22 is going to be 106. Boom. And then down 6 and down 16 more. I don't know why I put 20. It should be 22. Let's see, that's down 6, down 16. 6 plus 16 is 22. So again, minus 22. And let's see, from 84 to 62 is again minus 22. That absolutely looks linear. So the distance remaining in the bicycle trip was modeled by definitely is a linear function, because for every 1 it goes down, it's going down the same amount down here. Boom. It is indeed a linear function. Look at that. Okay, back to the back side of that page. We're not doing really any writing here. Just want to show you guys. We're talking about x-intercepts and y-intercepts. Now, keep in mind, this is the x-axis right here, the horizontal. And we see this line goes through right here at negative 2, 0. The x-intercept of a linear function as an ordered pair is negative 2, 0. Crosses right there. And in a linear function, you're only going to have one x and one y-intercept total. Y-intercept's different. A y-intercept as an ordered pair is right here where it crosses the y-axis, and that's at 0, 3. Notice that at at an x-intercept, our y is always 0. We've talked about this a lot, and at our y-intercept, our x is always 0. It's one of the ways you can find it. Plug in 0 for x, and you're going to get a y-intercept when you solve it. Plug in 0 for y, you'll get an x-intercept when you solve it. Okay. How about with nonlinear functions? Look right here. Notice with the nonlinear function, we still only have one y-intercept at 0, 3, but we have two different x-intercepts where it crosses. We have one at -3, 0, and one at 1, 0. Again, both where y equals 0 and the y-intercept where x equals 0. Okay. Let's take a look at a couple more slides, see what happens. All right. We see the x-intercept of a linear function. Oh, this is just what we went through. It's a graph of that, so we don't need to do that. I just went through that live. Just another look at this, guys. You see we have our x-intercept right there at 0, 0. Where's our y-intercept? It's still at 0, 0. So notice, whenever it crosses through the origin, that is both your x and y-intercept going forward, okay? All right, use the graph to estimate the x and y-intercept. Well, I see down here, the x-intercept's at 1, 2, 3, so that's 3, 0. Or they just want us to say the number. And our y-intercept's at -1, 2, 3, 4. So -4. Let's check it. Look at that. Okay, select the best estimate for the x and y-intercepts of this function. Well, it looks like the y-intercept's right here at 1. So I'm looking for a y-intercept of 1, which is these middle two. And my x-intercept looks right here. What is that? 1, 2, 3. So at x-intercept at 3, y-intercept at 1, this is definitely B. Yeah. Good. All right, now let's take a look at intercepts on a table. These are actually much easier to identify. Just look for the zeros. Boom, boom. But let's read the situation and see what that actually means. Ricardo launches a rocket from a second-floor balcony. The rocket is equipped with an electronic altimeter. The table shows the height given by the altimeter after each second of the rocket's flight. So this right here is where x equals 0, and I'm at a height of 15. And that tells me at time 0, I am starting out at a height of 15. Does it show the height given by the altimeter after each second of the rocket's flight? Oh, it doesn't say 15 what, so we don't know. But it's starting out at 15. So it's on one of those little things that holds the rocket down so that it can shoot up straight off of it. And that would be our y-intercept. Now, the x-intercept is where the height hits 0. In other words, the rocket's gone up, it's turned around, it's come down, it's hit the ground. That's after 8 seconds, it hits the ground at a height of 0, right? Okay. Which we already talked through that. Boom. Part B. What is the meaning of the intercepts? We talked about that, so we are good. All right, so raffle. The junior class is selling raffle tickets to raise money for the prom. The table shows the number of tickets remaining to be sold at the end of each week. Okay? So we see here at week 0, so that's our starting point. They have 500 tickets, right? That's their start value. But we see down here where there's 0 tickets left, it took 5 weeks. So after 5 weeks, all 500 tickets are sold. So remember, an x-intercept is where y equals 0. So our x-intercept is actually right here at 5. And our y-intercept is right here. It's that start value, right, where x is 0 at 500. Boom. Yeah, is there a part B to this? Part B, select the best interpretation of the y-intercept. Well, the y-intercept is at 500, and that tells us there's 500 tickets to sell. So the class had to sell a total of 500 tickets. That's it right there. Let's go. Yeah, we just kind of walk you guys through a little bit of what the symmetry is. So we're going to talk about the concept of symmetry. So a type of symmetry is line symmetry, and here's what it looks like. See how a line goes through that so that one side completely maps on the other side when we cross over that line. The other type of symmetry that we have is going to be down here. This is point symmetry, and this is a rotation. So watch, right in the middle here, if we rotate this, it's going to completely map onto that exactly. And that is the difference. Those are point symmetries, okay? Awesome. Okay, so using that, let's take a look at this. is there anywhere I can draw a line to make this map on itself? Absolutely not. The same way, there's no point I can click on to rotate it onto itself, so this has no symmetry. Right here on this line, again, I could draw lines down the middle of vertical lines, but if I map this over, it's going to map over to here, and it's going to make a line that goes like that. That doesn't map onto itself. That means this doesn't have line symmetry. But what I could do is I could put a point right here and rotate it around, and it'll rotate onto itself. That's point symmetry. This has point symmetry. This one right here, I could put a line straight down the middle, down the vertex right there, and it would map onto itself. This has line symmetry. This is a parabola. Here's a cubic function. Notice I could put a point about right here, and it would map right over onto itself, or map this way onto itself. This has point symmetry. Let's check our answer. Boom, we got it. By the way, please notice these are things you need filled out in your paper. If you look back, see I filled out the different types of symmetry and even put an example point where we could do it, or the line right here. All right, with that said, we're all done. You understand symmetry and linearity. Peace out.